Welcome back to the deep dive. Today, we are not just analyzing another press release or, some shiny marketing deck. We are stepping directly onto a crime scene.
Or the site of a miracle, depending on your perspective.
Right, exactly. We are tackling the single most contentious topic that has set the battery engineering forums on fire for the last 3 weeks. We are looking at the impossible triangle, the battery trilemma.
Yeah, it really is the fundamental law of our industry.
Yeah.
Energy density, fast charging, cycle life.
Pick two.
Exactly, you get to pick two. In the thermodynamic reality we usually inhabit, if you want a battery that drives a car for 500 miles and lasts 20 years, it is going to take hours to charge because the electrode design has to be thick and dense.
You need that mass.
Right. And if you want one that charges in 5 minutes, you need thin electrodes for transport speed, which totally kills your energy density.
Right.
Or, if you push both.
You degrade the chemistry and the cycle life plummets. It's a zero-sum game of ion management.
Always has been. Until now.
Right. So then Donut Lab walks onto the stage at CES 2026 and essentially says, we choose all three.
Yeah.
They announced a single cell with 400 watt-hours per kilogram, 11C charging, which is 0 to full in about 5 minutes, and the number that really broke the internet, 100,000 cycles.
Which is just an extraordinary claim.
Yeah.
I mean, just to calibrate the room here, we know you guys listening aren't the general public. You are cell engineers, pack designers, BMS architects.
You know the math.
Exactly. You know that 100,000 cycles is effectively immortality in electrochemical terms.
Yep.
A standard NMC 811 cell might give you, 1,500 to 2,000 cycles before hitting 80% state of health?
If you're lucky and manage the thermals perfectly.
Right. So Donut Lab isn't claiming an incremental improvement here. They're claiming a paradigm shift of 2 orders of magnitude.
Naturally, the skepticism was immediate and visceral. We've all seen the comments. Fraud, vaporware, physics violation.
Oh, yeah, the forums were brutal.
But today, we are moving past the hype. We're moving past the glossy renders. We actually have a specific document in front of us. It is the Comparative Solid-State Battery Analysis V1.
And this is based on the independent test report VTT-CR00009226 from the VTT Technical Research Center of Finland, dated February 9, 2026.
And VTT is a serious institution.
Very serious. This isn't a paid influencer review on YouTube. They're a government-owned research center with incredibly rigorous metrology standards. If their calibration equipment measures 286 amps, then 286 amps actually flowed through that circuit.
And this is the crux of our discussion today. We have to meticulously separate what VTT actually measured versus what is being extrapolated or, honestly, totally unverified.
That is the key distinction we need to make.
So that's our mission for this deep dive. We're going to dissect the verdict from this analysis, which is summarized as 1 vertex proven, 2 unknown. We need to separate the verified charging kinetics from the unverified density and life claims.
And we are going to try to reverse engineer the likely chemistry inside this black box based on the voltage curves and thermal signatures provided in the raw data.
Let's start with the vertex that we can actually put a check mark next to, the charging speed. Because the numbers in this report are aggressive, even for a solid-state prototype.
Highly aggressive.
So moving into section 1 here, the verified vertex. Let's look at the VTT test conditions. They tested a single 26 amp-hour pouch cell.
And we need to pause right there.
Yeah.
Because this is huge.
The format.
Yes. A 26 amp-hour pouch. A lot of these academic breakthroughs happen on coin cells, CR2032s with micrograms of active material.
Right, where heat dissipation is basically irrelevant.
Exactly. Scaling from a coin cell to a 26 amp pouch is where 99% of novel chemistries die. They fail due to resistive heating, uneven current distribution, edge effects. This is a relevant automotive-grade format, and they absolutely hammered it.
They ran baseline tests at 5C, which is a full charge in roughly 12 minutes. But the headline number, the one everyone is fighting about, is the 11C test.
Right, 11C.
Let's contextualize this for a second. For those used to standard EV charging, where a 3C rate is considered ultra-fast, DC fast charging, 11C means you are pumping current into the cell at a rate that would mathematically fill it in roughly 5.5 minutes.
Yep.
In this specific test, VTT pushed 286 amps into a single pouch cell.
286 amps. I just want that to sink in for the hardware guys listening. That is welding current.
Literally.
That is enough current to melt a standard set of jumper cables if you hold it too long. When you push that kind of current density into a porous electrode, you usually run into massive polarization immediately.
Because the lithium ions pile up at the electrolyte-anode interface.
Exactly. Solid-state diffusion is the rate-limiting step. The ions can travel through the current collectors and the liquid or solid electrolyte pretty fast, but getting them to actually intercalate into the anode structure takes time.
And when they can't get in fast enough.
The overpotential skyrockets. The voltage spikes. You hit your upper voltage cutoff, let's say 4.3 volts, almost instantly.
And then the charger thinks the battery is full.
Right. It cuts the current to save the cell. And you look at your actual capacity, and you've only put in maybe 10 or 15%. That's the classic false charge phenomenon common in high-rate testing.
But that is not what happened here. The report highlights a critical engineering metric that proves it wasn't a false charge: capacity recovery.
This is the single most important data point in the first section. After these massive high-rate charge events, the capacity recovery remained between 98.4% and 99.6%.
So it actually held the energy.
It proves the cell isn't just taking the current and dissipating it as heat, or worse, plating metallic lithium on the anode surface.
Let's talk about the plating for a second, because at 286 amps, lithium plating is usually guaranteed.
Guaranteed. In a conventional liquid electrolyte graphite cell, if you hit it with 11C, the ions can't intercalate into the graphite layers fast enough, so they just reduce right on the surface as metallic lithium dendrites.
And that lithium becomes dead weight.
It becomes electrical isolated. You lose that capacity permanently. So the fact that VTT could discharge this cell afterward and get 99.6% of the energy back proves that the intercalate or deposition mechanism is actually keeping up with that 286 amp input. It's not plating dead lithium.
Okay, but let's unpack the 11C label a bit, because the report mentions a constant voltage taper. It's not 286 amps from 0 to 100% state of charge, is it?
No, and it almost never is in any safe charging protocol. This is a standard CCCV profile. Constant current, constant voltage.
So they hit it with the fire hose first.
Right. They hold 11C, that 286 amps, until the cell voltage hits the upper safety limit. Then, to prevent overvoltage and completely breaking down the electrolyte, they hold the voltage steady at that ceiling while the current tapers off.
And even with that taper, VTT verified that it hit 80% state of charge in 4 minutes and 27 seconds.
Which is astonishing. That is legitimate fast charging. That is comparable to refueling a gas tank.
It is. But here is where it gets really interesting for the chemistry detectives listening today. There is a glaring voltage discrepancy in this report.
The 4.3 volt issue.
Exactly. Donut Lab's marketing sheets, the stuff they handed out at CES, say the operating window is 2.5 volts to 4.0 volts. But VTT tested this thing from 2.7 volts up to 4.3 volts.
And this is a massive clue. In battery forensics, the voltage window is the fingerprint of the cathode material. You cannot fake it.
It's just thermodynamics.
Right. Electrochemistry is dictated by the redox potentials of the transition metals involved. You can't just wish a material to operate at a higher voltage.
So why does that 4.3 volt upper limit tested by VTT matter so much?
Because it allows us to start ruling out suspects. If you were running a sodium-ion battery, which a lot of people suspected because of the no lithium marketing.
Yeah, that was the prevailing theory on Reddit.
Well, sodium generally caps out around 4.0 volts. Sodium transition metal oxides just aren't typically stable at 4.3 V without massive electrolyte degradation. They oxidize and fall apart.
What about LFP?
Same thing. Lithium iron phosphate has a very flat, stable plateau at 3.2 V and tops out around 3.65 V. You physically cannot push standard LFP to 4.3 volts. You'd destroy the cell before you got there.
So all those rumors about this being a cheap sodium-ion cell, the voltage curve basically kills that theory.
Completely. Unless Donut Lab has invented a completely novel, ultra-high voltage sodium cathode that literally nobody in academia has seen yet. A 4.3 volt cutoff strongly suggests there is a nickel-rich cathode in there.
Like NMC.
Very likely NMC nickel manganese cobalt, perhaps NMC 811, or even an ultra-high nickel chemistry. It strongly points toward a lithium-based system on the cathode side, or perhaps a very advanced hybrid, but certainly not standard sodium chemistry. The redox potential just doesn't lie.
Okay, so we have a cell that can take a massive punch of current and operates at a high voltage, but where does the energy go? I mean, internal resistance creates heat, and usually in our industry, heat is the enemy.
It is public enemy number one.
Which brings us to section 2, thermal dynamics. Because reading this part of the report, it felt wrong.
This was the most surprising, and frankly the most alarming part of the VTT report for me. The cooling setup.
Passive cooling.
Yeah. They didn't use active liquid cooling. They just clamped a cell between two aluminum plates, and the temperatures got high.
Extremely high. During the 11C charge, the cell surface temperature hit 89 degrees Celsius and 90 degrees Celsius. In fact, test number 6 was actually interrupted because it hit the 90-degree safety limit set by the lab.
90 degrees Celsius. For context for the pack designers, most battery management systems in modern EVs will heavily throttle charging if the pack hits 45 or 50 degrees Celsius.
90 degrees is scalding. Water boils at 100.
If you get a standard NMC 811 liquid electrolyte cell to 90 degrees, you are entering the danger zone for catastrophic thermal runaway. The organic carbonate solvents start to vaporize and create internal gas pressure.
The cell swells up like a balloon.
Exactly. And the separator, which is usually a thin polyethylene or polypropylene film, starts to soften and lose its mechanical integrity. If that separator melts, the anode touches the cathode, you get a hard internal short, and the cell goes up in flames.
But here, the cell survived. And not only did it survive, it actually seemed to like it. The VTT report notes that the one-sided cooling test, which essentially allowed the cell to get even hotter, was actually faster and more efficient than the two-sided cooling test.
Right, and this brings us to the Arrhenius relationship. This is the smoking gun for solid-state chemistry.
Okay, let's unpack that for everyone. The Arrhenius equation.
It's a fundamental principle from physical chemistry. The Arrhenius equation basically states that the rate of a chemical reaction or a transport process increases exponentially with temperature.
So hotter equals faster.
Yes. In standard liquid electrolytes, conductivity is already great at room temperature. But in solid electrolytes, whether that's ceramics, polymers, or sulfides, ionic conductivity is often the primary bottleneck. The lithium ions have to literally hop through a rigid solid crystal lattice.
And that takes energy.
Activation energy, yes. So when you heat the material up...
You provide that thermal energy.
Exactly. The lattice vibrates, the hopping mechanism becomes much easier, and the ionic conductivity skyrockets. In many solid electrolytes, ionic conductivity doubles for every 20 or 30 degree increase in temperature.
So by letting the cell get hot, Donut Lab wasn't just being lazy with their thermal management. They were strategically using the I²R heat to lower the internal resistance.
That's my read on it. The heat wasn't a waste product to be managed. It was an active mechanism to enable the speed. The resistive heating raised the cell temperature, which lowered the impedance, which allowed the cell to accept that massive 11C rate without hitting the 4.3 V voltage cutoff too early. It's a self-optimizing system in a way.
But as an engineer, isn't that living on the razor's edge? I mean, 90 degrees.
Oh, it is a massive engineering critique I have of this system. Sure, hot is good for solid-state conductivity, but operating at 90 degrees leaves you with absolutely zero margin for error.
Right. If your absolute safety cutoff is 90 and you are operating at 89...
You are one minor sensor glitch away from potential failure. Now, to be fair, Donut Lab claims no thermal runaway, meaning even if it fails, it won't catch fire.
Which implies the electrolyte is non-flammable.
Likely a ceramic or a high-temp polymer, yes.
But we haven't seen the nail penetration or crush testing data to actually prove that safety claim yet. We are just taking their word for it.
And there's a flip side to this heat preference, right? If the chemistry loves 90 degrees Celsius, how does it handle a Finnish winter? Donut Lab claims it operates at minus 30 degrees Celsius.
That is the paradox. That is what keeps me up at night trying to figure this out. An electrolyte that follows Arrhenius behavior, meaning it gets exponentially better when hot usually freezes up and has terrible conductivity when it's cold. The activation energy barrier becomes insurmountable.
The ions just stop moving.
Exactly. So, claiming incredible high temperature performance and incredible low temperature performance implies an exceptionally flat conductivity curve across a massive temperature range. Or perhaps a completely different mechanism entirely, like an internal self-heating architecture. Let's talk about the cost of that speed, efficiency. Moving to section 3. Because thermodynamics dictates you have to pay a toll for that kind of performance.
Right. There is no free lunch in electrochemistry.
Yeah.
We have to look at the round-trip efficiency, or RTE. At a standard 1C rate, this cell is excellent, about 92% efficiency.
Meaning for every 100 watt-hours you put in, you get 92 back out.
Yes. That's standard for a good Li-ion cell.
But at 11C...
It drops to about 82%.
So 18% of the energy is just lost.
Yes. And at 286 amps, that 18% loss is almost entirely Joule heating. P equals I²R. That totally explains why the cell shot up to 90 degrees Celsius so fast. It is generating massive internal heat.
So even if the cell can take the current, you are wasting almost a fifth of your energy just to charge fast. From a grid perspective or a charger perspective, that's a lot of wasted electricity.
It implies significant internal resistance at those high currents, despite the Arrhenius benefit we just talked about. And this leads us to a quick calculation on power density. Even without knowing the mass of the cell, which we will get to in a minute, charging at 11C implies massive power capability.
What are we estimating here?
We are estimating somewhere between 3,000 to 5,000 watts per kilogram during charge.
That is huge. That's comparable to supercapacitors or those ultra-high power LTO cells used in hybrid buses.
It is. But there is a gaping hole in the VTT data here, a massive blind spot. VTT only tested charge rates. The discharge in the report was limited to 1C.
Wait, really? I missed that on my first read. So we know it can take energy incredibly fast, but we don't actually know if it can let it out fast.
Correct. And for Donut Lab's announced partners like ESOX Group, who are making specialized military drones, discharge is literally everything. You need that burst power for takeoff or evasive maneuvers.
You can't just assume symmetry.
Absolutely not. Just because ions can endure being shoved into the anode quickly, whether that's intercalation or plating, doesn't mean they can exit the cathode quickly. The de-intercalation reaction kinetics can be vastly different.
So for the drone engineers listening, do not sign the purchase order just yet until you see a high-rate discharge curve.
Precisely. We need to see a 10C or 15C continuous discharge curve to confirm the power density is bidirectional. Until then, it's just a really fast-charging battery that might discharge like a standard EV cell.
All right, let's move to the elephant in the room. The metric that everyone wants to know but VTT didn't explicitly report. Section 4, the unverified vertex energy density, the mass mystery.
This is the most frustrating part of the entire 40-page report. VTT reported the absolute energy capacity about 91 watt-hours, but they didn't report the mass or the volume of this cell.
They had the cell physically in their hands, in their lab. Why not just put it on a scale?
Likely because the client Donut Lab tightly defined the scope of the test. If the contracted scope was verify charging speed and thermal behavior under high C rates, VTT wouldn't necessarily characterize the gravimetric density unless asked. It's a black box test.
They test what they are paid to test.
Right. But we can do some forensic detective work here.
Okay, let's run the scenarios, pull out the calculators. Donut Lab claims 400 watt-hours per kilogram.
Right. So if we know the cell holds 91 watt-hours for it to hit that 400 WHKG claim, the cell must weigh approximately 227 to 230 grams.
Do we know how big it is physically?
Based on some pretty intense video analysis of the cell sitting in the VTT test clamp, comparing it to the standard Arbin connectors and the thermocouple cables visible in the frame, the community estimates it to be about 170 millimeters by 70 millimeters by 10 millimeters thick.
Okay, so 17 by 7 by 1 centimeter. That's roughly 119 cubic centimeters of volume.
Exactly.
Okay, stick with me on the math here. If the volume is 119 cubic centimeters and it needs to weigh 230 grams to hit the target,
that implies an overall cell density of roughly 1.9 to 2.0 grams per cubic centimeter.
Is that a realistic material density for a solid-state cell?
It depends entirely on the chemistry you assume is inside. Let's look at the options. Scenario A, a polymer or composite electrolyte. These are basically functionalized plastics like PEO or similar matrices. They are very light. Density is usually around 1.2 to 1.6 grams per cubic centimeter.
So if it's a polymer...
If it's a polymer, the whole cell would likely weigh around 190 grams, and the energy density would actually be higher than their 400 claim. It might be hitting 460 WHKGs.
Wow, okay, so a polymer chemistry easily fits the physical math. What about scenario B?
Scenario B, oxide ceramics. Things like LLZO, lithium lanthanum, zirconium oxide. That stuff is heavy. Its true density is around 5 grams per cubic centimeter. A cell made with a thick LLZO ceramic separator would likely weigh over 300 or maybe 350 grams.
And that drops the energy density down.
Significantly, down to maybe 260 or 300 WHKG. Still very good for a fast-charging cell, but not the breakthrough 400 number they put on the slide deck.
And scenario C, just a conventional liquid lithium-ion baseline.
Standard liquid electrolyte cells with copper current collectors on the anode and graphite are usually around 2.6 to 2.8 grams per cc. That would yield about 250 WHKG.
So for the 400 WHKG claim to be true, it basically has to be a lightweight cell architecture. No heavy steel casing, no thick oxide ceramics, maybe not even standard copper foils.
Exactly. It points heavily toward a polymer-based or a sulfide composite system. And we actually have a real-world benchmark for this to compare it to, Canino.
Right, they have a commercially available solid-state cell.
Yes, a 27 amp-hour cell. Very similar capacity to this 26 Donut Lab prototype.
How does the Canino cell compare on weight?
The Canino cell weighs 263 grams.
Yeah.
For Donut Lab to hit their target of 400 weight coulombs, they need to be about 30 grams lighter than the current state-of-the-art Canino cell.
So it is physically plausible.
It is plausible, but it leaves very little room for packaging overhead. They can't have heavy structural clamps or thick laminated aluminum casing. They likely need to use thinner current collectors, maybe metallized polymers or aluminum, instead of copper on the anode side, assuming the anode chemistry allows for it without alloying.
Which brings up volumetric density, because volume matters just as much as weight for motorcycles and cars.
Yes. Even if we argue about the weight, the volume is objectively small. 91 watt-hours in that 119cc pouch implies over 750 watt-hours per liter.
That is extremely competitive.
It's elite. That is up there with the best liquid NSC 811 cells and QuantumScape's published figures. So even if they miss the weight target slightly, the energy per size metric is world-class.
Okay, so energy density is plausible but unverified. Now we get to the one that makes my head hurt. Section 5, the impossible vertex. Cycle life.
100,000 cycle.
It sounds like a typo. When I first read the press release, I thought they accidentally added 2 zeros. Most commercial EV batteries are rated for 1,000 to maybe 2,000 cycles. Donut Lab says 100,000. But the VTT tested 7 cycles.
Right, 7. And here's where we run into what the engineering community is calling the 694-day problem.
Do the math for us. Why is this physically impossible to have actually tested?
Even if you could charge the cell in 5 minutes and discharge it in 5 minutes, which is an incredibly aggressive 12C continuous profile and assumes absolutely zero rest time for thermal equalization, a single full cycle takes 10 minutes.
Okay, 10 minutes per cycle.
100,000 cycles times 10 minutes is 1,000,000 minutes. That is roughly 694 days, almost 2 full years of nonstop, 247 cycling.
And Donut Lab, or at least the subsidiary Nordic Nano, hasn't even existed long enough in this current corporate iteration to run that test continuously.
Exactly. Unless they have a literal time machine in their lab, they haven't physically tested a cell to 100,000 cycles. It must be a model-based extrapolation.
So they ran it for, what, a month?
Probably. They ran it for a month or two, maybe saw zero observable capacity degradation, or measured an incredibly flat Coulombic efficiency, like 99.999%, and then just projected that linear curve out to infinity.
But is that valid in battery science?
It's incredibly risky, because degradation mechanisms change over time. You might have zero apparent degradation for 1,000 cycles, and then suddenly microcracks start forming in the solid electrolyte due to mechanical fatigue, or a dendritic short finally pierces the separator, or the contact pressure relaxes and fails. Battery death is rarely a straight line. It's often a cliff.
Let's talk about why batteries die. For the newer engineers listening, why is 100,000 cycles so hard to achieve?
It's mostly mechanical. Volume expansion. When you charge a battery, you are literally shoving physical lithium ions into the anode matrix.
It takes up space.
Yes. If your anode is silicon, it expands by up to 300%. Even graphite expands by about 10%. And if it's a lithium metal anode, which you generally need to hit 400 Wh/kg, you're actually plating metal, growing a physical layer of lithium, and then stripping it away. That expansion and contraction is like the cell is breathing.
And solid materials don't like to breathe.
Exactly. Imagine a rigid concrete wall. Now imagine something inside the wall trying to expand by 10% every few hours. The wall cracks. If you have a rigid ceramic solid electrolyte and a breathing anode, eventually something is going to crack.
Or the interface delaminates.
Right, it peels apart. At 11C charging, that mechanical stress is violent. You are stripping ions so fast you create voids, empty microscopic spaces at the interface, leading to loss of electrical contact. Once you lose contact, the cell resistance spikes and the cell dies.
Is there any battery chemistry on Earth that actually lasts 100,000 cycles?
There is one that gets close. LTO, lithium titanate oxide. Toshiba makes them, the SCID cells. They reliably last 20,000 to maybe 45,000 cycles.
Why do they last so much longer than everything else?
Because LTO is what we call a zero-strain material. The crystal lattice is a specific spinal structure. When lithium ions go in and out of that lattice, the unit cell dimension barely changes. It expands by maybe 0.2%.
Yeah.
It doesn't breathe. It's rock solid, mechanically stable forever.
But. There's always a but.
The but is that LTO has terrible energy density, maybe 80 or 90 Wh/kg at the cell level. Because the operating voltage is so low, Donut Lab claims 400.
So this is the central paradox of this whole deep dive. How do you get LTO-like mechanical cycle life with lithium metal-like energy density?
This connects us perfectly to the Nordic nano hypothesis. We know from corporate filings that Donut Lab invested heavily in this company, Nordic Nano Group, and their published expertise is in TiO2 titanium dioxide nanostructures.
And TiO2 is chemically related to LTO,
Yeah,
right?
very closely. It's the same fundamental chemical family. If they're using a nanostructured TiO2 anode, that would absolutely explain the cycle life, zero strain.
And the charging speed.
It would explain that too, because nanomaterials have massive surface area. The ions have thousands of pathways to intercalate instantly. It would also explain the no lithium marketing claim they initially made on the anode side.
But the density.
That is the conflict. Typically, nanostructures have terrible tap density. They are fluffy. To get a total cell energy density of 400 waste kilogram with a fluffy TiO2 anode, the cathode would have to be spectacularly, unbelievably energy dense, or the electrolyte layer would have to be microscopically thin. This is the biggest technical mystery of the whole report. The cycle life claims and the energy density claims seem to fight each other based on known physics.
So we have dissected the vertices. Let's try to look inside the box. Section 6, the black box chemistry. What are we actually looking at here?
We have a few concrete clues now. We have the upper voltage cutoff at 4.3 V, the thermal behavior where it likes 90-degree heat, the lightweight requirement, and these manufacturing clues.
Let's touch on that not lithium-ion phrasing they use in their PR.
It's very careful lawyering. Saying not lithium-ion usually means not the conventional slurry-cast graphite anode with a liquid carbonate electrolyte system.
So it's a distinction of architecture, not necessarily the active ion.
Right. It allows for a lithium metal battery. It allows for solid state. But it distinguishes them from the old legacy tech.
And are likely candidates.
Well, we definitively ruled out sodium due to the 4.3 voltage. And we ruled out pure heavy oxide ceramics due to the density requirement.
What about the screen printing clue? This came from folks digging into Nordic Nano's patent history.
This is huge for both cost and physical structure. Standard batteries are made in gigafactories with massive roll-to-roll coating machines and 50-meter-long drying ovens. It's called slurry casting. Screen printing suggests you are laying down very thin, precise layers, anode, electrolyte, cathode, almost like printing a graphic on a t-shirt, but with functional nanomaterials.
If that's true, it completely explains the cheaper-than-Li-ion claim. You don't need $1 billion factory to start production. You just need high-precision printers.
Exactly. CapEx goes way down. It also supports the thin layer hypothesis required for high energy density. If they can print a verified 10-micron solid electrolyte layer that is completely defect-free and doesn't short out, that's the holy grail of solid-state manufacturing. A thin electrolyte means less internal resistance, which means faster charging, and less dead weight, which means higher density.
So, synthesizing all this, putting it all together, what is your best guess as a cell engineer on the internal architecture?
Based on the hot as good Arrhenius data, the 4.3 V cutoff, and the lightweight requirement, I suspect we're looking at a composite electrolyte, probably a polymer matrix to give it flexibility and processability, heavily doped with ceramic fillers like LLZO nanoparticles to give it mechanical strength and stop dendrites.
Paired with what?
Paired with the standard, very mature, high-voltage NMC cathode. Now, the anode is their secret sauce, likely that nanostructured Ti2 we discussed, or maybe a heavily engineered silicon-carbon composite that mimics LTO zero-strain behavior but holds way more energy.
A composite polymer ceramic. That fits almost all the data.
It fits the data we have. It doesn't mathematically prove the 400 Wh/kg array, but it perfectly explains the 11C charging speed and the thermal resilience at 90 degrees.
Let's zoom out to the broader industry reaction. Section 7. Industry credibility and the skeptics.
Because people are actively angry about this announcement.
Oh, the legacy industry is furious. The CEO of Svolt, which is a major Chinese battery manufacturer, went on record and called it a fraud. Straight up.
And Hackaday did a huge piece basically saying the physical math doesn't add up. They did a chemistry elimination bracket saying no known material does all three vertices.
And you know what? It's a completely fair critique based on current literature. If you look at standard battery textbooks, this material does not exist.
Yeah.
But that is literally what innovation is, finding the material behavior that isn't in the textbook yet.
Right.
I always remind people who say something is impossible. People said blue LEDs were physically impossible for decades until Akasaki, Amano, and Nakamura figured out the specific gallium nitride crystal growth process. Then suddenly, it was everywhere. But here's the counter evidence to the skeptics. Look at who else is chasing these exact numbers. Toyota, Samsung, SDI, CATL. They all have published roadmaps targeting these exact specs, 400 Wh/kg, solid state, Fast charge for around 2027 or 2030.
Exactly. Donut Lab isn't claiming to violate the fundamental laws of physics. They are simply claiming to be 3 or 4 years ahead of Toyota's R&D schedule. That is ambitious, maybe a bit arrogant, but it is not physically impossible. Startups with highly focused teams often move much faster than massive conglomerates.
And they say they are shipping now, like Q2 2026.
That is the defining difference. Toyota says 2028 for limited rollout. Donut Lab says we are putting this in a commercial motorcycle in April.
Which brings us to their PR rollout, the I Donut Believe strategy. They are releasing this validation data bit by bit. Episode 1 was the VTT charging report. Episode 2 is coming up.
It's a brilliant, highly annoying marketing strategy. It forces all the skeptics to actively engage. It keeps them dominating the news cycle for months. But it deeply frustrates engineers like me who just want the full, unfiltered data sheet. Just show me the discharge curves.
But the ultimate verification isn't going to be a PDF report anyway. It's the Verge TS Pro, the electric motorcycle they are partnering on.
This is the put up or shut up moment for the entire company. If that bike ships to real customers in April, we will know the truth immediately.
How? Just by riding it.
By basic physics.
Right.
We know exactly how much the chassis of that bike weighs. We know the aerodynamic drag coefficient. We do the promised highway range. You cannot fake gravity and wind resistance. If the bike hits the 200-mile range numbers and doesn't weigh 500 kilos, the energy density is real.
And the charging.
If a reviewer can pull up to a standard CCS fast charger and pump it full in 10 minutes, the charging is real.
You can't fake it when a customer is literally riding the product.
Exactly. The motorcycle is the ultimate, undeniable verification instrument. It bypasses all the lab theory.
Moving to Section 8, manufacturing and the Valley of Death. Because it's one thing to make a pristine, hand-built 26 prototype for VTT to test, it's an entirely different beast to make 10,000 of them a week for motorcycles.
This is where battery companies die. The Valley of Death. Look at Natron Energy or Freyr. Scaling up is brutal. You run into yield issues, microscopic contamination, delamination on the roll-to-roll line. But there's one specific detail in the VTT report that gives me genuine hope for their scaling ability. No clamping.
Explain that for the listeners. Why is clamping pressure such a big deal in solid state?
Most solid-state batteries like QuantumScape's early prototypes need massive external pressure to work. You have to squeeze the pouch cells with thousands of psi to keep the solid layers physically touching. Because as the anode breathes and expands, it loses contact with the rigid electrolyte.
And that means the actual battery pack in the vehicle needs heavy steel braces and hydraulic tensioners just to hold it together.
Which totally kills your pack-level energy density. You might have a 400-weight HH's cell, but if you need a 50-kilogram steel vice grip to hold it together, your car gets heavy and inefficient.
Ooh.
But VTT explicitly noted they tested this cell with minimal external pressure, just light contact to conduct electricity to the bus bars.
If that holds up at the pack level, that is a massive, massive weight saving.
Huge. And it radically simplifies pack manufacturing. If you don't need hydraulic presses and high-tensile steel bands in your battery pack assembly line, you cut cost and complexity drastically. It suggests the internal interface chemistry is sticky or compliant enough to hold itself together under cycling.
Which again supports the polymer or composite hypothesis we discussed earlier. Polymers are flexible.
Exactly.
So we've unpacked the VTT report, the chemistry, the skeptics, the scaling. Let's bring it all home, the outro.
The initial verdict stands. 1 vertex proven, 2 unknown.
Proven. Fast charging. 11C is real. It takes the 286 amps, it stores it, it recovers it. The thermal efficiency takes a hit, but the electrochemistry works.
Unknown. Density and life. We have very solid, educated guesses that the density is physically plausible if they use light materials like braided polymers. But the cycle life, that 100,000 number, remains the biggest red flag. The math just doesn't support that they've tested it physically. It has to be modeled.
So what does this all mean for the listener? Why should a pack designer care today?
Here's the so what. Let's play devil's advocate. Even if Donut Lab completely misses the 400 kilo mark, say they only hit 300, and say they completely missed the 100,000 cycles, say they only hit 5,000 cycles.
Which is still more than double a standard EV cell.
Exactly. A 300 kilogram cell that charges in 5 minutes and is inherently safe at 90 degrees Celsius. That is still an incredibly commercially viable product that revolutionizes military drones, that revolutionizes electric motorcycles. They don't actually need to hit every single crazy marketing number to be a massive financial success.
That is a great point. Perfection isn't required for disruption.
No, it's not. They just need to be tangibly better than what we currently have. And the
Yeah.
charging speed alone, assuming the discharge matches it, is better than what we have.
Here is my final provocative thought for everyone to mull over. The entire industry is waiting for the second episode of their I Don't Believe PR series on March 2nd. We analyzed the charging. But what if the next video is just a scale?
That's it. Just put the damn cell on a digital scale. That single undeniable data point mass solves the energy density mystery instantly. If it weighs 200 grams, the skeptics lose. If it weighs 400 grams, the 400 weight TT claim is dead in the water.
It really is that simple. We will be watching closely. Until then, I encourage you to go download the raw VTT data yourself. It's linked in the show notes. Dig into the curves. Stay skeptical, but stay curious. Thanks for listening to The Deep Dive.
See you next time.